Hello students, in this session we are going to study the shear stress distribution in I section. We have a I section, uniform I section, in which equal flanges are there. The length and thickness of flanges are equal. And there is a web of thickness B. The thickness of the web is B. The flange thickness or width is capital B. The depth of the web is small d, and the entire depth, capital D, is the total depth of the I section, right? And we have to draw shear stress diagram for this I section, shear stress diagram. So how should we proceed? We know the shear stress formula, that tau will be equal to F A y bar by IB. This is our standard formula for finding the shear stress. But here the cross section is changing. Here it is a rectangular cross section of different width and thickness, and here the web have different dimensions, right? So we can divide our entire problem into two parts: the shear stresses in the flange and shear stress in the web. So we will do this problem into two parts, right? First we will find out the shear stress in the flange, and then we will find out the shear stress in the web. So first we are doing the shear stress in the flange. For that, what we can do is we can take a section, a small element like this. Suppose this we have taken a small section, we have taken a strip, we have taken at a distance y from the neutral axis. This is our neutral axis, this is center of gravity or centroid, and from here at a distance of y, we are taking a section strip, that is this strip we have taken, right? And we have to find out the shear stress in this strip, and that will be valid for the flange section, right? So section of this flange section, it will be valid, right? So we will take the area of this strip. What is the area of this strip? And then y bar, the centroid of this from the neutral axis, and centroid will be lying at this point. Suppose this is G1, right? So centroid of this flange, right? So what will be y bar and what will be the area of this strip? So area of the strip in the flange, that will be equal to this area. This will be equal to, now what is this thickness multiplied by the width, and width is capital B. The width of the flange is capital B. So capital B, this width is capital B, known to us, and for flange this is uniform. For flange, entire flange, it is uniform. Flange is the upper part. So capital B multiplied by the strip, this thickness, capital B multiplied by this thickness, and this small thickness will be equal to d by 2 minus y, this distance minus y, so d by 2 minus y. So area will be equal to B multiplied by d by 2 minus y. This is the area of this small strip. Now we want to find out the y bar, the moment of this area, centroid of this area from the neutral axis, y bar, so that we can find out moment of this area, right? So y bar will be equal to, what is y bar? Y plus this small thickness, right? Half of this part, small half of this thickness plus y. So this will be y plus half of this thickness, total thickness, d by 2 minus y, right? So this will come out to be half of d by 2 plus y, half of d by 2 plus y. So it will come out to be d by 4. So this is the centroid, distance of centroid from the neutral axis, and this is the area. Then what is a y bar? A y bar, which is to be used here, a y bar. So that will be equal to, a y bar will be equal to B d by 2 minus y half d by 2 plus y, right? So half d by 2 plus y, right? So this is a y bar. We can put it in the shear stress formula. So tau will be equal to f a y bar, which is b times d by 2 minus y half d by 2 plus y divided by I times b, width here is capital B, it is general formula, that's why small b, but actually it is capital B. So I multiplied by capital B, right? So this is the shear stress. Solving this, I am writing directly the answer. So what is the final result of this? So this will come out to be f by 2i, b to b cancel. So this will come out to be f by 2i d square by 4 minus y, d square by 4 minus y. So this is our shear stress distribution. So tau will be equal to f by 2i d square by 4 minus y square, and this is a parabolic distribution. For flange, we are talking about only flange, right? This is valid from small d by 2 to capital D by 2, right? So this is valid for flange only. We are talking about only flange, not for web. This is for flange only. We have taken section on the flange only, and here we have not taken any section. So tau is the shear stress distribution is parabolic, right? And when the distance y is d by 2, the shear stress is 0. So at y is equal to capital D by 2, shear stress is 0. It means shear stress is 0 at the outer fibers. So if I take the outer fiber here, if this is a line on which shear stress to be drawn, so at these points, outer fiber shear stress is 0. At capital D by 2, the shear stress is 0, right? Shear stress is 0 at capital D by 2. And at y is equal to small d by 2, the extreme edge of the flange, right? So at y is equal to small d by 2, tau will equal to this value, put here small d by 2. So f by 2i d square by 4 minus d square by 4. So this is the maximum value of the shear stress in the flange. This is basically the maximum value of the shear stress in the flange. Say this is tau 1. Maximum. This is not the maximum value of the entire section. This is the maximum value of the shear stress in the flange only. We are talking about the flange only, right? So this is the maximum shear stress in flange, right? Extreme flange, right? But there is a section when the flange joining, right? So we are talking about only flange part of this section. Taking only flange part. We are taking only flange part, not web is connected. Flange part. There is no web part is connected here, right? Yeah, means just at the top of the flange where there is when the web and flange are meeting, at just point where there is only flange and no web section is just started, right? So shear stress is parabolic, and this value is the tau 1 value here. So at the flange we are getting some shear stress like this, right? Here like this, right? Here, right? So this is the maximum value of shear stress in the flange only. We are talking about flange, right? This value, and this value is tau 1, which is this value, right? So this is the value of maximum shear stress in the flange, tau 1. This value is tau 1. maximum shear stress in the flange, we are taking on the flange, and web is not just started, right? So this is how we can find out the shear stress in the flange part of I section. So this was the first part, shear stress in the flange, that we have taken first the strip in the flange, area of this strip, y bar of this strip, a y bar moment of this small strip, and then shear stress using this formula f a y bar by ib. Using this formula, the shear stress distribution is parabolic, like it was in rectangular section, so it is parabolic. And inside the web, where y is equal to d by 2, just at the point where web and flange are meeting, inside the flange, not inside the web, where the flange and web are meeting. So at y is equal to d by 2, shear stress distribution is this. This is the maximum value of the shear stress in the flange at a point where flange and web are meeting, right? So this is the shear stress, that maximum, and we are talking, this is tau 1, which is given by this value, right? So this is how we obtain the shear stress distribution in the flange. Now we will study the shear stress distribution in the web part of I section. In continuation, we want to find out the shear stress distribution in the web part. We have already found out the shear stress in the flange. Now we want to find out this small width B, thickness B, this part, the web part of this I section, what is the shear stress distribution? And we have already obtained the shear stress distribution in the flange part, and it was like this, parabolic distribution was this, and maximum value of the shear stress in the flange where the flange and web were meeting was tau 1, which is given by this value. Tau 1 was f by 2i, and this in bracket value, right? So this is a shear stress distribution in flange. Now we want to find out the shear stress distribution in web. Shear stress in web. For that, we will take a section so that, because we have to take the section from the upper part, right? So we will include this part as well as web part. Both parts should be included, because we have to take any section which is at the top fiber, right? So here basically two parts are included, right? One is, some part is in web and some part is in flange, right? So this we have taken a small strip or small section, right? And we have to find out the this moment of area of this part, So we can divide this area, this part, into two parts. One is the flange part, and second is the part which is distributed in the web, and this is at a distance of y from the neutral axis, right? So what we can do is, we can find out the moment of area of this part, this total part. This can be divided into two parts. One is the flange, so that will be equal to a1 area of the flange, y bar, plus area of the part section which is in web, so that is a2 multiplied by y2 bar, moment of area of this part, right? So what is a1 y1 bar? So a1 is the area of the flange, and what is width is b, and what is thickness of this flange? That is capital D by 2 minus small d by 2. So that will be capital B, capital D by 2 minus small d by 2. This is the area. And what is y1? y1 bar, basically centroid of this flange. Centroid will be acting at the center, which will be half of this thing, right? So this will be half of d by 2 minus d by 2, right? Plus y plus d by 2 plus d by 2, right? A small d by 2 plus this thickness. So there is something wrong in this. So y1 will be equal to small d by 2 plus small d by 2, this thickness, this length, plus this part, right? We have to reach to G1. Basically, right? So this is d by 2 plus half of this part, thickness. So half of d by 2 minus d by 2. This is y1. So this is a1 y1. We have to use it here. a2 y2. a2, what is a2? Area of the section which is in web. That section which is available in the web, right? Which is hashed in the web. So A2 will be equal to, this thickness is B, width is B, and this thickness, this is small d by 2 minus y, small d by 2 minus y. So this A2 will be equal to, width B multiplied by this thickness, that is small d by 2 minus y. This is the A2, and Y2 bar will be equal to Y2 bar. This here, somewhere here, there is centroid of this section, G2 suppose, right? So distance of this centroid from the neutral axis. So this will be y plus half of this. So this will be y plus half of this thing, d by 2 minus y, right? So this is just mathematics. You can use this seeing the diagram. So this is A1 y1 bar, A2 y2 bar. Solve it and you will get AY bar. So AY bar will be equal to, AY bar will be equal to this multiplied by this. So B d by 2 minus d by 2 multiplied by this. This is d by 2 plus half of capital D by 2 minus small d by 2. This is A1 y1 bar plus this part A2, which is B d by 2 minus y multiplied by this part, this is y plus half d by 2 minus y. So this entire value is AY bar, right? Isn't it? So this entire value is AY bar, right? And then we have to find out the shear stress, and shear stress we want to find out in the web. So width of the web we will be taken B. So here small b will be taken because we want to find out the shear stress in the web only, right? So tau will be equal to F AY bar by IB. AY bar is this value divided by IB. So solving this is F. AY bar is this value, entire value, this value we will put here, that is AY bar by IB. Solving it, we will get the shear stress in the web section. I am writing directly the value of shear stress, right? And that will be equal to, I am writing directly the value of shear stress, and that will be equal to shear stress distribution F by IB. B is the width of the web, F by IB, B by 8, d square minus d square. After solving, I am writing the direct value. When you solve it, you will get this value, right? Shear stress AY bar value when you solve it, and IB is the in the denominator and F is in the numerator, right? B by 8 d square minus d square plus B by 2 plus small b by 2 bracket start d square by 4 minus y square. So d square by 4 minus y square. I have written directly the value of shear stress in the web. This is the shear stress distribution in the web only. Shear stress distribution in the web. And you can see here, this is again a parabolic distribution. So this is parabolic distribution in web, right? And the point where web and flange meets, that is the small d by 2. So put y is equal to small d by 2 and you will get the shear stress at this point, right, in the web, at this point in the web where flange and web meets, and the shear stress in the web, right? So at small d by 2, right? So what you are getting is, so shear stress at a distance y is equal to small d by 2, at y is equal to small d by 2 where the flange and web meet, but in the web, where the flange and web meets, and the point just at the web side, right? So y will be d by 2. Put in this equation. Suppose this equation is number 2. So put into the value of y is equal to d by 2. You will get only this value. So you will get the tau at the web. Suppose this is tau 2. That will be equal to f by ib, b by 8, d square minus d square. So this is the value of shear stress in the web. In the web where the flange and web meet, right? And this was the value of tau 1 where the flange and web meet inside the flange, right? At same point d by 2, these two values are there. It means there is abrupt change in shear stress. Abrupt change in shear stress from tau 1 to tau 2. So there is abrupt change in shear stress from tau 1 to tau 2. So suppose this is the value is, this value is tau 2, right? So this is shear stress at the same point, this is at the point where web and flange meet but in the flange, and this is the shear stress where the web and flange meet but in the web. So this is tau 2. So this is tau 1, this is tau 2. Tau 1 is this value, tau 2 is this value, right? So this is tau 1 and this is tau 2. Is it okay? And tau is 0 at the base, hit this point, right? So this is how the shear stress, and it is a parabolic distribution, and where it is maximum, so shear stress will be maximum at y is equal to 0. When y is equal to 0, shear stress will be maximum. So at y equal to 0, tau is tau max, and put it here and you will get the maximum shear stress. Then what is the value of maximum shear stress? So solve it and you will get the maximum shear stress. So what is the value of maximum shear stress? That will be equal to f by ib, that is b by 8, d square minus d square, plus bd square by 8. So this is the maximum shear stress in the entire I section, which is at the center where y is equal to 0, right? At the center. In this case y is equal to 0. So this is the maximum shear stress. Okay. This is the tau max, maximum shear stress, right? So this is the shear stress distribution, parabolic distribution inside the web, This is maximum shear stress inside the flange where the web and flange meets, right? Inside the flange. And this is the maximum shear, the shear stress where web and flange meet but inside the web, right? This is tau 2. And this is the maximum shear stress in the entire I section, which is just at the entire center of the I section.